Alright guys, in this video we are going to talk a little bit more about the Henderson-Hasselbalch equation and how it can be used to find the pH of buffer solutions and the pH of buffer solutions after you've added a strong acid or a strong base. So the first thing you need to know is what the equation is itself. This is the equation. The pKa, that means the negative log of the Ka, just like pH is equal to the negative log of the H plus concentration. Something to know about this ratio here, this can be used in moles or in concentration as molarity. It's really the ratio between the base and the acid that makes it effective, so just keep that in mind. So a note about this equation, it can only be used if you can make the assumption in your ICE table. So remember, the criteria for that is if you multiply your Ka by 100 and you get something less than the starting concentration, you're good to make the assumption. So we can only use this equation if that is the case. So the first way we can use this is to use it to find the pH of a buffer, and we can use it just like it is. We don't have to modify the equation at all to find the pH of a buffer. So let's take a look at an example of that. So we have, let's see, a question asking us to find the pH of a solution containing 0.5 molar acetic acid and 0.5 molar sodium acetate, and it gives us the Ka for acetic acid. So the first thing we're going to do is ask ourselves, is this going to act as an acidic or basic buffer? And the answer comes from whether or not you're starting with an acid or a base, essentially. So right now we're starting with acetic acid, so this is going to be an acidic buffer. So we want to write then what the dissociation reaction would look like for this acid right here. So writing out that equation, and I'm showing you guys the long way to do this first before we apply the Henderson-Hasselbalch equation. So there's two ways to do all of these. This is the long way. I'll show you the shortcut in a second. So I want to point out to you guys, we are using sodium acetate, but what that means is when this sodium acetate hits the solution, it's going to dissociate into the sodium ion and then the acetate ion. Sodium's not going to do anything for the pH. What we're really interested in here is this acetate ion. That's going to provide the conjugate base for acid. Okay, so here's the reaction, what it does in water. We fill in what we start with in our ICE table, so we are 0.5 molar here, 0.5 molar there. We have no H+. This is the regular old ICE table that you guys are used to. You fill in what you don't have. Notice, guys, there's a 0 here in the products. That means we're going to be shifting toward products, and so we're going to have our plus x's on this side. And then we'll have our minus x on this side. So fill in the change column, fill in the equilibrium column, and then if you guys notice, our Ka is small enough that we can make the assumption. So you guys see I've crossed out my x's here to make the assumption, plugging that into the K expression, solving for H+. I can find my H+ concentration and then take the negative log of that to get the pH. Okay, so really this is something you guys have been doing for quite some time. The only real addition here is that you're starting with a little bit of the conjugate base, so you just have to include that in your initial column. Okay, otherwise this all looks familiar, hopefully, to you. So that's the long way. If you want to use this Henderson-Hasselbalch equation to solve this problem, you can. All you have to do is plug in what we're given. So this is the Ka, so we take the negative log of it to get the pKa. And then we have the log of the base on top, which is the conjugate base right here that was provided, and then the acid on bottom, which was the acid that was provided. So plugging all that stuff in, and we get the pH. So instead of doing, like, I don't know, 7 steps, you're doing maybe just a couple in your calculator. Okay, so this makes it super easy. As long as you're paying attention to what's the acid and what's the base, you'll be fine. Another example, this is something that we haven't gone over yet, is how to find the pH of a basic buffer. So let's take a look at this. Okay, a basic buffer is a buffer that uses a base to make the buffer. So what I mean by that, if you take a look, find the pH of a buffer containing 0.5 molar NH3 and 0.4 molar NH4Cl. So in this case, we've got NH3 floating around and NH4Cl floating around. When this guy dissociates, it's going to make NH4 plus and Cl minus. Comparing the NH4 plus and NH3, NH3 is got a larger Kb, meaning this is going to act as a basic solution. Okay, So plugging this into the long way, okay, so recognizing that our salt is going to separate into these two ions and the chlorine is worthless, so we ignore it. This is what our reaction is going to do. Okay, so this is just a basic reaction. Remember, all bases have to react with water. So when NH3 reacts with water, we get NH4 plus and OH minus. We use our ice table. We plug in what we are given of the base up here and the conjugate acid right here. We don't have any OH minus, but that's what's going to use to determine the pH. We had to include water in the reaction, but we don't include it in the ice table because it's not included in equilibriums. We fill out which direction the equilibrium is shifting. If you guys notice, we had a 0 here for the OH minus concentration. So that means that we're going to have a shift toward the products. And so we have our plus x's over here. Fill in our equilibrium column. We can make the assumption, so cross out the x's. Plug into our Kb expression. So OH is here, NH4 plus is here, NH3 is here. Solving for it, the x, that's the OH minus concentration. And so that can get us the POH if we take the negative log of it, and then 14 minus, that will get us the pH. Okay, so very similar in steps, but we have to remember to write the correct equation for bases in reaction with water instead of acids. Okay, so again, that was the long way. The short way uses the Henderson-Hasselbalch equation. So here's that. So the first thing, remember, the Henderson-Hasselbalch equation uses the pKa, not the pKb. So we have to find the Ka before we can use this formula. So finding Ka, you have Kw divided by Kb is equal to Ka. Okay, that's a 10 to the negative 10th power. So then we can plug all that stuff in. So we've got the pH is equal to the negative log of the Ka, plus the log of the base on top and the acid on bottom. So notice, guys, I've paid attention to what's my acid and what's my base and made sure the base got on top and the acid on bottom. And that got me my, my pH. Okay, so far, pretty simple. I hope this is providing you a shortcut and not stress, because it really does come in handy to make your life easier. Okay, other uses for the Henderson-Hasselbalch equation. When we have buffers, the whole point of a buffer is to resist the change in pH of a strong acid being added or a strong base being added. So there's a couple of changes that we can make to the Henderson-Hasselbalch equation to adapt for that. So the beginning stays the same. pH is equal to pKa plus the log. Base is still on top, acid is still on bottom. But if we're talking about the addition of a strong acid, what we're going to do is have, this is the base from the buffer, this is the acid from the buffer, and then this is the amount of acid that was added. Okay, what I mean by that is the strong acid. Okay, and we're going to use that number in moles, not in concentration. Same goes for adding a strong base to a buffer. It's still going to be pH plus equals pKa plus the log of base over acid, and in this case we're going to have the added base on top and on bottom and in moles. Okay, I do want to point out something. Notice, guys, the base up here, so if we're adding a strong acid, the acid will react with the base in the buffer, and so what we're going to do is basically diminish the amount of base in the solution, and when it does that, it's going to turn into the acid, which is why we have this minus the acid and added the acid. Likewise here, if we're adding a base to a buffer, the base will be reacting with the acid in the buffer, diminishing the amount of acid that there is, and adding to the amount of base that there is. So that's why we have those plus and minuses here. Okay? So I know this kind of sounds like a lot of talk. Let's see what an example looks like. So adding strong base to a buffer. So let's see. Okay, so we have a question that asks us to calculate the pH of a 1 liter solution of 0.5 molar acetic acid and 0.5 molar sodium acetate, to which 0.010 moles of sodium hydroxide has been added. And they give us the Ka of our acetic acid. So likewise, I'm going to show you guys the long way first. 1, to recognize how awesome the short way is, and 2, to understand why we do the short way. The long way, when we're adding acid or base, we have to actually do 2 different ice tables. Okay? So the first ice table, whenever you're adding acid or base to a buffer, you just have to turn everything into moles, and that's going to be the same across the board. So that's what I'm going to do first. I'm going to start my starting stuff, I'm just basically turning it into moles. So I have a 0.5 molar acetic acid. It's in a 1 liter solution, so that means I have 0.5 moles of acetic acid. Likewise for the sodium acetate. Once I've done that, I can plug into my equation. Now notice, this is not the equation of the dissociation of the acid in water. This is the reaction of the weak acid with the added base. Okay, so this is not the reaction we're used to seeing. This is basically like the play-by-play, what's going to happen when you add the base into our acidic buffer. So we're going to start out with 0.5 moles. Okay, this entire table is in moles. 0.5 moles of our acid and 0.5 moles of our conjugate base. And the question says we're adding 0.010 moles of strong base in there. And remember, the only important part about strong base is the OH minus. So that's why I'm ignoring the Na from that strong base. Okay, so we have to ask ourselves, before we even find out what's going to happen in the change column, think about it. We have a base being added to a solution that has this ion and that ion. Okay? Between these two ions, is OH minus going to react with this guy or with that guy? Okay? So obviously the base is going to react with the acid. So what that means is the amount of acid is going to go down, and then the amount of conjugate base will go up. So that's why I have this guy completely disappearing, because it's going to completely react. And this number going down, and this number going up, so that we can have our equilibrium values here. Okay, so that's because the base reacted with the acid. So this number goes up, down, this number goes up. So once we're at this point, we can now have new numbers for our amount of acid and our amount of base in our solution, and that's going to affect the pH. So now comes our second ice table that looks a little bit more familiar. Okay, now we're going to do the dissociation with water. Now that all of the OH minus has reacted, we take a look at the mess that's been left over. So from the previous ice table, from that guy right here, the amount of acid we've calculated is 0.49 moles. The amount of conjugate base we've calculated is 0.51 moles. That's why these numbers appear where they are. We don't have any OH minus floating around yet. Because there's a 0 here, that means we are shifting this direction with the equilibrium. So we're plus x's here, minus x here, and then fill in our equilibrium column, cross out the x's, and then plug into the K expression to solve for x, and that will get us the H plus concentration, and from there we can find the pH. Okay, so that was a lot of work. We can absolutely save ourselves some time by using the Henderson-Hasselbalch equation instead. I want to remind you guys, this is a really important table. Okay, you have to mentally be able to do this part before we can do the Henderson-Hasselbalch equation. So keep in mind, if I'm adding base, that means my amount of acid is going down. If I'm adding base, that means my amount of conjugate base is going up. You have to keep that concept in mind. So let's take a look at what we're doing for a Henderson-Hasselbalch equation. Everything still has to be in moles, so you would have had to do that first step again anyway. And then we plug in pH is equal to negative pKa, or negative log of the Ka, plus the log of the base. So this was our original base, and this was our original acid from the very beginning of the problem, and this was the added base, and added base here. So notice we're adding the base here and subtracting it here, so the number of acid moles go down and the number of base moles go up, and we end up getting the same pH. Okay, so I really want to draw your attention to something. Ooh, where is it? Okay, notice how these numbers reflect what happens in these columns. Okay, so that's not a coincidence. This column is reflected here on bottom, and this column is reflected here on top. So really, you're doing a lot of the same work, it just is put in a different format. Okay, but don't get confused by what goes on top and what goes on bottom. I feel like that's probably the most confusing part about doing the Henderson-Hasselbalch equation. The last situation that we've got to talk about is adding strong acid to a buffer. So if you take a look at this example, we're going to see a basic buffer. This is the same basic buffer we looked at the other time. We've got NaOH and then NH4+, which is going to be floating around after it dissociates. And we're adding 100 milliliters of strong acid. Okay, so again, I'm going to show you the long way and then the short way to do this. So to go about this the long way, the first thing we have to do in these adding acid and base problems is to transfer everything from molarity into moles. So we're going to do that for all three of the things. So we have a 0.25 molar NH3, so that's half a liter, so multiply 0.5 times 0.25, you get this many moles of NH3, and so on. Okay, so turning all of those into moles. The next thing we have to do is take a look at how this basic buffer is going to react when we add the acid to it. So remember, HCl, the only really important part of HCl when you're adding it to the solution is the H plus that comes off. So if you take a look at the reaction that's going to occur, we've got the base reacting with the H plus to form the conjugate acid. Okay, so I'm making my ice table like that. Initial moles of my base and then initial moles of my conjugate acid. And again, that's from what I found up here, okay? And then initial moles of my added acid, okay? So HCl really means H plus in this case. Alright, so we've got that plugged in. We have to figure out, okay, which way is the equilibrium going to shift, that way or this way? So that's when you have to stop and ask yourself, what is this H plus going to react with in solution? Is it going to react with the NH4 or is it going to react with the NH3? And hopefully by now we all have memorized that NH3 is acting as a base, so it would interact with the H plus. So because we know these two will react together to form more of this, the equilibrium will be shifting toward the products. So that's how we know to add our given number of moles of our H plus. That gets added to the product side and subtracted from the reactant side. So that's the change column, the change row, and then we can fill in what the equilibrium is going to look like. Okay, so that's the first ice table. Again, the first ice table is always for what the reaction is going to look like between your added substance and what's already in your solution. Okay, so now we need to figure out what's going to happen with the pH that we've changed the concentration of the base and the conjugate acid. So that's when we're going to write the dissociation reaction between the base, what happens when it goes into water. So here's our base, it reacts with water, makes NH4 and then OH minus, which dictates the pH. We plug in from our answers from the previous ice table, we plug in now what's floating around in the solution. So because of our previous answers, we know we have this many moles of base and this many moles of acid. We don't put any numbers in for the water column, and we have 0 OH minus to start out with. Because there's a 0 here, we know we're shifting toward products, and so we're going to have our plus x's here, minus x's here, fill in our equilibrium row, make the assumption, plugging into the Kb over here, we're going to have our x, our 0.25, and then our 0.075. That will solve us for the OH minus concentration. From there we can get the pOH, and then from there we can get the pH. So this was a lot of work, okay? So obviously there's an easier way to do it, and it goes back to knowing about this ice table. So recognizing that if I add 0.05 moles of acid, it's going to react with 0.05 moles of base and disappear and turn into 0.05 moles of conjugate acid. Okay, knowing that how that's going to react is really important for the Henderson-Hasselbalch version. Okay, so here's the short way. So if you're going to do the short way, everything still has to be in moles. And also the short way involves the Ka, and we've been given the Kb in this problem, so we have to find the Ka. And then from there we can plug in what we found earlier. So we're going to have pH is negative log of the Ka, plus the log, and this is the tricky part. This was the original base, because remember, base goes on top. NH3 was the base, so moles, original number of moles of base minus moles of acid added, and then this was original number of moles of acid on the bottom plus added acid over here, and that will get us our pH for the addition of strong acid. Okay, so go ahead and get to work on the additional problems I've given you, and hopefully everything will do well.